Dolphin Learning. Hi, welcome back. So today we'll be calculating the present value and future value of general annuity due using the formula method. So I'll quickly explain the type of annuity it is, how the formula is derived, and then we'll do some examples for present value and future value. So with that being said, let's get started. Okay, so here's a quick recap of annuity due from the types of annuity video. What is an annuity due? Annuity due is when the payments are made at the beginning of each payment period. So let's assume that you're making an investment as shown in this timeline for the next 6 years, and you're investing $600, and your payment period was from January 1st to December 31st. The payment would be due on January 1st of each year, and it would begin when you initially signed the annuity or initially signed the contract. So it would begin right away as soon as you sign it. And the last investment would be on January 1st of year 5th, with subsequent investments being on January 1st of year 1, year 2, and so on and so forth. But the last one is on January 1st of year 5th. Now, there are two types of annuity due. There's a simple annuity due and a general annuity due. In a simple annuity due, the interest compounding frequency and the payment period frequency are the same. So what that means that if the interest is being compounded on an annual basis, the payment is also being made on an annual basis. If the interest is being compounded on a semi-annual basis, payments are being made twice a year, semi-annually, so on and so forth. Now the topic of this video, which is general annuity due, in this situation, the interest compounding frequency and the payment period frequency are not the same. They're not equal to each other. So if this one's monthly, this one's quarterly. If this one's semi-annually, this one's annually, right? They're not the same. So what we'll have to do is we'll have to calculate a new interest rate that matches with the frequency of the payment period. And when we do that, we'll be able to calculate the present value and the future value of general annuity due. So let's go ahead and see how the formula is derived so that we can calculate the general annuity due questions that I want to get to. Okay, so here's the formula that were generated in the simple annuity due video. If you haven't checked that out, I highly recommend it because it builds on the core concept of annuities. So we generated this formula in that video. It shows you how they're derived. Today what we're going to look at is a little bit of tweaks and twerks to make this formula functional for a general annuity due formula. The current reason why it's not a functional formula for general annuity due is because the payment frequency here and the interest frequency here are the same. That makes it a simple annuity due, but in general annuity due, they're not the same. So that what we will have to do is we'll have to calculate a separate interest rate that will match the frequency of the payment so that we could go ahead and solve for the general annuity due. And to do that, what we'll have to do is we'll have to use a nominal to effective interest rate formula. I've also made a video on this concept. This is also required for your knowledge, so I highly recommend that you check that out as well. But how this formula comes about, I've made a video on it. Anyways, we use this formula. We'll substitute I for I2 because this I2 will be used to match the frequency of the payment. So we'll substitute the I with I2 and we'll get a general annuity due formula, right? So the only thing we've made a change from the simple annuity due formula to get to the general annuity due formula is substitute the I. And the reason why we had to substitute the I and to change the I in this situation was so that this I2 matches the frequency of the payment. So again, there's nothing else that's changed. Everything else has remained same. Now we've generated the formula. Now let's go ahead and look at a quick example and get ahead with that one. This question states that Ellie is investing $2,100 at the beginning of each month for the next 2 years. The investment earns 4% compounded semi-annually. What is the total value of her investment at the end of 2 years? Now, the first thing we have to do is draw out a timeline with any time value of money question. But before we even get to that, We just need to understand the concept of the question. So here it's telling us that she's investing $2,100 at the beginning of each month. So we know that it's an annuity due question, and the investment earns 4% compounded semi-annually, which we're going to put into a timeline. And we need to figure out if it's a present value or a future value. But in this case, it's asking us to calculate the end of 2 years. So we're calculating the future value of the annuity, right? Because we're asking to calculate the total value of her investment at the end of 2 years. So with this information, let's generate a quick timeline. So we generate the timeline, or draw the timeline. We see that we have the interest rate, which is from 0.1, or starting in month 0 all the way up until month 24. We have a monthly investment of 2,100, 2,100, 2,100, all the way up until month 24. Now you might ask, how do we get month 24? It's 2 years that the total investment is being made for, and it's being made on a monthly basis, right? 2,100 at the beginning of each month. So 2 times 12 months in a year gives us 24 months of total investment. Now, what I'd like to point out here is that we can clearly see that the compound interest for semi-annually, which is 4%, the interest rate, and the payment period frequency are not the same, right? We see that because the interest is being compounded at 4% semi-annually, and the payment period frequency is 2,100 monthly, which tells us, since they're not the same, which tells us that it's a general annuity due, and we have to do a nominal to effective interest rate conversion of the interest rate, of the 4% interest rate, to get to a monthly rate so that we can calculate a general annuity due future value. So let's go ahead and start converting the 4% semi-annual rate to a 4%, or not a 4%, to a X% of a monthly rate. To do that, we're going to use the if interest rate equation, which is I2 is equal to 1 plus I1 to the power of M1 times M2 times time period, right? Now your I1 is your 4% compounded semi-annually, right? As given in the question. We're going to convert this 4% to a I2, which is going to equal to the monthly frequency. Now your M1, in this case, is the frequency of the 4% given in the question, or of the current interest rate that you already given to, or you already have. M2 is what the frequency we're trying to achieve, right? In this case, we're trying to achieve the frequency of 12, which is a monthly interest rate. And the time period, which is the last thing, which is 2 years, which is also given in the question. So now that we have all this information, we just have to plug it into our equation and solve for I2. So when we do that, we have I2 is equal to 1 plus 4% per annum divided by 2, right? It's always being divided by the frequency of the compounding frequency given in that question. So 4% divided by 2 to the power of 2, which is the compounding frequency multiplied by time in years. Now, there are multiple ways. It's up to you how you like to simplify the formula. I would do it in a very ordinary fashion where I would actually multiply 2 times 2 and then 12 times 2 to get to 4 over 24, right? Some people just cross out the 2's here and just left with 2 over 12. It's how you do it, but for the purpose of this video, I'm just doing it as 4 over 24. And we've also divided part of the brackets where we simplified the 4% divided by 2, which gives us 1 plus 2%. And then we simplify that even farther. We get 1.02 to the power of 4 over 24 minus 1. We simplify that even farther. We get 1.02 to the power of 0.1 with a recurring decimal place, 6 all the way up until 7, right? So there's a line at the top. Anyways, when we take that to the power of, when we take 1.02 to the power of 0.166666666, whatever it is, we get the answer of 1.0030589. Subtract 1 from that, and we get a 0.030589 per annum interest rate. Remember, this is a per annum interest rate. It is yet to be multiplied by the compounding frequency of 12 to get to the compounding interest rate. So when we multiply that by 12, when we multiply this interest rate by 12, we'll get a compounding monthly rate of 0.0396706,839. So technically 3.96706,839%. So now that we have this interest rate, now what we have to do is plug it into our equation. Now that we have calculated a monthly compounded interest rate, all that is left for us to do is to use the future value equation and substitute in the variables for it. So let's go ahead and list out the variables and the unknowns. So to begin with, we don't know the future value. That's what we're trying to calculate. Makes sense. We have a payment of $2,100, right? Because that's being made at the beginning of each month. So that's right. And we have N, which is 12, which is, where do we get 12 from? Because that's the monthly payments. Multiply that by your compounding frequency, multiply that by your time frame, number of years, which is equal to 2, which gives us number of payment is 24. So that's how we get that. I2 we have already calculated. So let's use this variables given to us, plug it into the equation, solve for FV. So I'm going to plug in the compounded monthly equation. Here I've converted it into a percent form, because that's how I like to visualize it. If you like to use decimals, go right ahead. But anyways, here it's in a percent form. And as you can see, it's being divided by the compounding frequency of 12 because the interest rate was the I2, the new interest rate is now being compounded on a monthly basis. So that's why we're dividing by 12. The last one was being compounded on a semi-annual basis. Anyways, so we just plug that into our equation, top, bottom, and this side. We also plug in the 2,100 for payment and 12 times 2 for our N, which is going to equal 24. Let's go ahead and simplify it even farther. So when we do that, we get 2,100 for payment. And then we simplify this fraction, and we get 1.00335, 1.0033058,90325 to the power of 24 minus 1. This fraction is the same as this fraction, so we get the same answer there. This fraction is also same as this fraction, except there's not 1 being added at the bottom, so we get 0.0033058,90325, right? So then we simplify it even a bit farther, where we take it to the power of 24, and we'll get something like 1.0824321600094 minus 1 divided by nothing changed at the bottom, nothing changed on this side of the equation, nothing changed on this side as well of the fraction. And then we got 2,100. Now the next thing is to just simplify it even a bit farther. So we're left with 0.0824321600094. When we subtract 1 from that, when we subtract 1 from the equation, left with that, and then we divide it by 0.0033058,90325. We're going to get something like 24.93493,489,06183 multiplied by 2,100, multiply that by 1.0033058,90325, and we get the final answer of Ellie's investment at the end of 2 years, which will equal to $52,536.47 approximately. Okay, so now that we have done this question, let's go ahead and look at a present value question and solve that one. Okay, so this question states that Amy received a custom bank loan to start her business and is required to pay $1,800 at the beginning of each quarter for the next 3 years. If her loan has an interest rate of 3.5% compounded monthly, what was the initial amount of the loan? Okay, so before we draw out the timeline, which is the first thing to do, there are a few things that we need to note. What we know already is that it's an annuity due question because she's making $1,800 worth of payments at the beginning of each quarter, And what we know is that it's for the next 3 years, so the time frame is for the next 3 years, and the interest rate on the loan is 3.5% compounded monthly. So let's go ahead and put this information into a timeline. Okay, so when we put it into a timeline, what we see is that it's 3.5% compounded monthly throughout the whole period. Starting in quarter 0, the payment's at 1,800, going all the way up into quarter 12. How do we get quarter 12? It's for 3 years, then the loan is for 3 years, with each payment of 1,800 being made at the beginning of each quarter. So there are 4 quarters in a year. Multiply that by the number of years the investment is, the number of years for the loan is being used for. We get 12. 4 times 3 gives us 12. Now, how do we know that it's a general annuity due or a simple annuity due? So when we take the interest compounding and the payment period and we put it together, we see that they're not equal to each other because the interest compounding is at 3.5% monthly, whereas the payment frequency is at 1,800 quarterly. Since they're not the same, we know that it's a general annuity due, and we'll have to do a calculation for the interest rate of 3.5% compounded monthly to change it into a quarterly rate, a conversion, change it into quarterly rate, so that we can go ahead and calculate the present value of the loan. And again, I'll like to repeat it. How do we know that it's a present value? It's asking us to calculate what was the initial amount of the loan. So that's how we know that it will calculate the present value of the whole question. So now let's go ahead and use our nominal to effective interest rate formula to convert the 3.5% compounded monthly into a quarterly rate. To do that, we're going to simply use the nominal to effective interest rate equation. I've already explained the variables here. So in this case, I1 is going to be 3.5% compounded monthly. Your M1 frequency, which is given in the equation, frequency of the 3.5, which is 12. Your M2, the frequency that you're trying to get to, a quarterly frequency, which is going to be 4 quarters in a year. Time frame is 3 years, right? With this information, we plug it into our equation, and we get 1 plus 3.5% divided by 12 to the power of 12 times 3 multiplied by 4 times 3. Again, 12 is the monthly frequency of 3.5%. 4 is the frequency that we're trying to achieve. 3 is the number of years given in the question. Now, let's simplify this even further. We get 1 plus 0. When we divide 3.5% by 12, we get 1 plus 0.00291, with a 6 being recurred for whatever long period, to the power of 36 divided by 12. We simplify this even farther, and then we get 1.002916, because we added the 1, to the power of 36 divided by 12 minus 1. And then we just simplify it even farther. So when we divide 36 by 12, we get a power of 3. We take 1.002916 to the power of 3. We get 1.008775546. Subtract 1 from that, and we have a per annum rate of 0.008775546 per annum. It's being compounded quarterly, which is the frequency we're trying to achieve here. So we're going to multiply it by 4. And when we multiply that by 4, we get 0.03510218258 compounded quarterly. So this is the interest rate which we're going to use in a present value formula to calculate the total value of the initial loan that Amy received. Let's go ahead and do that. Okay, so now that we have calculated a compounded quarterly rate, all that is left for us to do is to use our present value of general annuity due equation and substitute in the variables for it. So the equation states that present value is equal to PMT into 1 minus 1 plus I2, which we calculated, the compounded quarterly rate, to the power of negative n divided by I2 multiplied by 1 plus I2. Present value is unknown. That's what we're solving for. Payment is $1,800 per quarter. Your I2 is already given. And your N is 4 times 3 is equal to 12 again. 4 is the number of quarters in a year. Multiply that by time frame in a year. Total number of years, my bad, is equal to 12. That gives us 12. Now that we have all this information, put it into this equation, and then we get a present value of Amy's loan. So when we put it into our equation, we have 1,800 as payment, into the brackets of 1 minus 1 plus 3.50218, 258%, divided by 4. Again, it's dividing by 4 because it's compounded quarterly, to the power of negative 12. Same rate. I've changed it into a percentage because that's how I like to see it when I write down my equations. It's the same rate. Wherever I2 is in the equation, I've written the same rate, and it's being divided by 4. So when we simplify the fractions even farther, we get is 1.0087755454645. This fraction and this fraction are practically the same. So that's why we get the same inside of the fraction is practically the same. So we get the same answer there. The bottom fraction, we're just not adding a 1 to that. So that's why it's left as is, except, well, simplified and left as is without adding the 1. Now we simplified this part of the fraction even more with the power of negative 12, and we get 1 minus 0.900462127815 divided by the same thing. We've already calculated that. Multiplied by the same thing. We've already calculated that. Nothing changed except for this. So then we go ahead and simplify it even farther, where we subtract 1 from the 0.900462127815859, and we're left with 0.09953787218 divided by 0.0087755454645. When we simplify this even farther, nothing changed here, nothing changed here. So when we simplify this even farther, we're going to get 1,800 multiplied by 11.3426419514,681. Multiply that by nothing changed here as well. So you just multiply these together, multiply that by 1,800, and we'll get the total value of Amy's loan when she borrowed it, which was equal to $20,595.92 approximately. So that's all I had for this video. Thank you for watching. If you liked it, give it a thumbs up. Consider subscribing to the channel, as there's always engaging content coming. And check out related videos. Also, if you have any questions, comment down below and I'll try my best to address them.